In this video, I'd like to talk about the math question of the day for Saturday, July 22nd, 2023. And with this problem, we are evaluating this definite integral between x values of -1 and 2 of x to the third plus e to the 1/4 x dx. And integrals like these are typically seen in a Calculus 1 class. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through this. And just as a reminder, if we have some integral from a to b of g of x dx, and let's say we knew the graph of g of x, if it looked maybe something like that, then calculating this definite integral, we can call it a, since it's equal to the area between the bounds, let's say this is A and this is B, underneath this curve and between the x-axis. So this definite integral, remember, it's just calculating the area of a region just like this. And we could look at the graph of this function here and the bounds to get a better visual of what's happening, but this is the general idea. But when actually computing this, what we can first recognize is that we have a sum here. And when you're adding or subtracting terms in an integral, we can separate those into their own integrals. So we can rewrite this as the integral from -1 to 2 of x to the third dx plus the integral from -1 to 2 of e to the x over 4 or 1/4 x dx. And the reason we want to separate this is that we'll use different techniques for each of these terms. For instance, this first term here, this is just a cubic polynomial. We can use the power rule on that. So we get x to the fourth. We'll divide that by the new exponent. We just increase by 1 and divide by the new exponent. And then we need to evaluate this at the bounds between -1 and 2. And we'll come back to that. For this integral here, we'll need to do a substitution. We can set u equal to x over 4. So that du is 1/4 dx, or if we put the 4 on the other side, we have 4 du is dx, and we can directly substitute there. So we get the integral, and we'll come back to the bounds, but we have e to the u multiplied by dx, which is now 4 du, so we can put the 4 out front. And with the bounds, we can either plug them in now and change them to bounds in terms of u, or we can just evaluate this integral and put everything back in terms of x, and then from there just use the original bounds. So let's take that approach, and we can use the fundamental theorem of calculus here. Once we have an antiderivative evaluated at the top bound, and then we subtract that antiderivative evaluated at the lower bound. So we plug in 2 first. We get 2 to the 4th over 4, then we subtract this evaluated at the lower bound. We get -1 to the 4th, which is just 1, and all of that divided by 4. And now we compute this integral. We find its antiderivative, which is just equal to the function. We get e to the u, but u is x over 4. And of course, this constant just carries along. And then we evaluate this at the original bounds between -1 and 2, since we put everything back in terms of x. Now on the left here, we have 16 over 4 minus 1 over 4, which simplifies to 15 over 4. And for this expression on the right, we plug in the top bound. We get 4e to the 2/4, or 1/2. And then we subtract this evaluated at the lower bound. We get 4e to the -1/4. So this right here will be our exact answer. But if you do want an approximation, you can, of course, plug this into a calculator and round it to whatever accuracy you prefer. But remember, this expression that we found, this again is just the area underneath this function between the x-axis and between these two bounds.